our second faculty seminar of the semester. Thanks everybody for coming out. I'll remind you that we have, in our usual way, one per month. So we have two more left in this semester. On November 7th, it will be Francois Morel, and December 5th, Melissa Lane. So please come back for both of those. And today, we have yet another fantastic speaker in our lineup, and that, of course, is Lynne Lu, who is currently the director of the Andlinger Center for Energy and Environment. Previous to becoming director, which was last year, 2016, she was the associate director for external partnerships, and among a number of other things, she began the E-Affiliates program, which is focused on industry interactions. Lynn comes from Princeton. She has her PhD from chemical engineering here in 2001. She then went off to do a few other uninteresting things, and then saw the light and came back to Princeton on the faculty. She works in a range of interesting topics, including organic and plastic electronics. And this includes flexible solar cells and circuits, and the work that she's going to talk to us about today, which has to do with transparent solar cells and how they form the basis of what is called smart window technology. So please join me in welcoming Lynne Lu.
Thank you, Michael, for that very kind introduction. And I'd also like to take this opportunity to thank Francois for the invitation. This invitation came probably a year ago now. So thank you. I know this is a little different from the typical flavor of your speakers in this series. So I hope this will be interesting to you. As I was reflecting back, as Michael said, I became director of the Andlinger Center a little more than a year ago, and since the outset, Francois and I have had many conversations about how best to articulate the differences and complementarity between Princeton Environmental Institute and the Andlinger Center for Energy and the Environment. I think we've made solid headway. There's still a lot of work to be done, so I'm looking forward to continuing those discussions with you, Michael. So if you'll indulge me, I'd like to take the first couple minutes to tell you a little bit about the Andlinger Center before we talk about smart windows. So the mission at the Andlinger Center is to develop solutions for energy and environmental future. And I think this complements very well the mission at Princeton Environmental Institute, which is to advance knowledge and to develop the next generation of leaders. In this world of limited resources, I think it makes sense for us to work together to capitalize on the talent, to capitalize on the resources that are available so we can really tackle some important and global challenges today. So to develop solutions requires multiple backgrounds and expertise. So here, what I'm showing is the research portfolio at the Andlinger Center. Research at the Andlinger Center can be categorized in 6 broad categories, and we have 115 faculty members and researchers spanning 40 departments, programs, and centers. Some of them are also associated with Princeton Environmental Institute, including myself. So of those 6 buckets, these 4 are core to our mission. Built environment, transportation, and infrastructure. So thinking about electric vehicles, for example, or desalination. Claire White's work in civil and environmental engineering on green cement technologies fall in this bucket. Forrest Megger's work on looking at energy efficient buildings, designs, and systems also fall in this category. And increasingly, our work in smart windows is moving us into this category as well. The second category is electricity production, transmission, and storage. So wind, solar, Barry Rand's work on thin film photovoltaics, Eggy Coleman's work on fusion, transmission. We have Min Ji Chen, who just joined us jointly with electrical engineering. He's interested in power electronics and how to efficiently transmit electricity. And then, of course, Dan Steingart, who's in storage. Fuels and chemicals is the third bucket. We're going to be burning fossil fuels for the foreseeable future, so how do we do this efficiently? And then, of course, there's work on producing advanced biofuels by Jose Avalos, where he does metabolic engineering of mitochondria. And at Pollutant Detection and Remediation Technologies, this bucket I'm immediately reminded of Mark Zondlo's work. He develops the sensors to detect contaminants in air and in water, and he deploys the sensors in field studies. So there's some overlap here with Princeton Environmental Institute. Not core, but equally important are these two research buckets because they help us assess whether these energy technologies can be adopted and what the consequences are of adopting these energy technologies. So decision science, policy, and economics, and this is in strong collaboration with the Wilson School's STEP program. And Elke Weber here is our bridge between the Andlinger Center and the STEP program. And then, of course, Princeton Environmental Institute, where you focus on the science of environment and climate change. We'd like to take cues from you so that we can think about developing the solutions that are necessary to curb climate change. So that's internal. We collaborate beyond the walls of Princeton University, and this is through Princeton E-Affiliates Partnership that Michael had just mentioned. This is a corporate affiliates program that's administered by the Andlinger Center, but it's really meant for anybody in the energy and the environment space. And if you've heard President Emeritus Shirley Tillman talk about Princeton E-Affiliates Partnership, she's referred to this program as the flagship corporate affiliates program on campus. We're super proud of that. So the goals of this program is threefold. It's a lower barrier for academic industrial collaboration, to promote technology transfer, and to enhance teacher, student, practitioner interactions. So thus far we have 6 companies. ExxonMobil came on 2 years ago as our charter member, pledging $5 million over 5 years. And that's our single largest membership contribution so far. And working with ExxonMobil, we've created this umbrella agreement to lower barrier for collaboration. So before this umbrella agreement, researchers at ExxonMobil can't collaborate with Princeton faculty. These one-off collaborations often take the better part of a year to negotiate before you can commence on the work. With this umbrella agreement in place, now the members and our faculty just have to identify a problem, identify a source of funding, and this project can proceed within weeks of figuring out what the problem is. So this has been really, really effective. And 2 years since they've become members, they've sponsored 11 projects, totaling about $4.5 million. And these 11 projects, some are connected to business units, but the majority of them really allow the researchers and our Princeton faculty to explore that evolving energy landscape. So they include the development of solar cell technologies, the development of battery technologies, with GFDL looking at Arctic sea ice, modeling Arctic sea ice melting, and also looking at carbon dioxide absorption in oceans. And then we're proud of this memorandum of understanding that we've signed with the U.S. Army's Picatinny Arsenal Garrison that allows for research partnerships. So they have a sustainability mission, and we do too, and we're working together to identify ways to sustainably dispose of spent munitions. So there's a lot of work to be done, and I think together we can make Princeton a better place, and together we can increase the impact of Princeton in this space. Okay? So with that, let me tell you about smart windows. This week is Nobel Week, so I thought it was fitting to introduce this community to these 3 Nobel Prize winners. This is Alan McDermott, this is Hideki Shirakawa, and this is Alan Heater. And they shared the Nobel Prize in Chemistry in 2000 for discovering conducting polymers. And this was really inspirational to me. So this was right about the time I was writing up my thesis, and I was trying to figure out what I should do next. And my thesis is on polymer physics, and this inspired me because this is a whole new class of materials that I could perhaps apply my polymer physics to study. They opened my eyes because plastics went from looking like this to looking like this, right? So this is an Oled TV. The organic light-emitting diode is made out of organic semiconductors, or polymer semiconductors. This is a flexible display. Its backplane has organic semiconductors. So the circuits that run the display has organic semiconductors. This is solar panels that's built on plastic and on cloth that's on a dome to provide portable power. So again, polymer and plastics and molecular semiconductors. This is out of University of Tokyo. This is a pressure-sensitive hand, right, a robot hand. And the pressure sensor is made out of organic transistors. And these organic transistors basically can read the pressure of somebody grabbing it. So these are the kinds of applications that the community envisions when they talk about plastics and organic semiconductors. So different from inorganic semiconductor like silicon, there are unique attributes associated with this class of materials. That includes chemical versatility. So this is from our collaborator, John Anthony at University of Kentucky. You can see that by adding subsequent benzene rings to the backbone of this compound, you can change its optoelectronic properties. And this might be useful if you were trying to tune the color of the light that's emitted in an organic light-emitting diode. It could be useful, as you'll see later on, when you're trying to tune the color of the light you're trying to absorb in an organic solar cell. And you can do that by simple chemistry. You can also conduct chemistry, and instead of tuning the backbone, you add side chains. And when you add side chains to the compounds, you now promote solubility in common organic solvents, or even in this case in water. These are organic materials and plastics after all, so they're lightweight, they're mechanically flexible, so you can envision printing them over large areas on plastic substrates, on cloth, on paper, to make your electronic circuits. So the community is really excited about these large area applications. Just to give you an example of what the chemical structures of these organic semiconductors look like, I'm showing you here a few. This is copper phthalocyanine. And copper phthalocyanine is actually a common dye that's used in the automobile paint industry. We know to first order how to tune the properties of these materials. By taking copper phthalocyanine, and we decorate copper phthalocyanine with fluorines on the outside, fluorine is electron withdrawing, so it basically lowers your molecular orbital. Now, instead of transporting holes, this has a stronger tendency to transport electrons. This is pentacene. You can buy it, and people have used it for 3 decades now to make organic circuits. But it's not solution processable, so you'd have to thermally evaporate it to deposit thin films out of it. But by adding these greasy side groups, now this pentacene molecule, called TIPS pentacene, is solution processable. You can put it in an organic solvent, make an ink or a formulation that you can then spread over large areas. This is poly-3-hexylthiophene. This N stands for the number of repeat units. So as N grows, the conjugation length along the backbone increases. You're effectively narrowing the band gap. Again, you're tuning the optoelectronic properties. And then these hexyl side chains, again, are added to promote solubility of this polymer. So to first order, you get a sense of how we can tune the optoelectronic properties, the solubility of these electrically active materials. So just how conductive are these materials? So I'm showing you here glass as an insulator, silicon as a semiconductor, and then you've got metals as conductors up here. The standard plastics that you're used to, nylon and Teflon, are down here. With conducting polymers and molecular semiconductors, you vary over an interesting range depending on the doping. Okay? And so that's what's interesting about these materials. You can actually vary the conductivity of these materials, ranging from being a semiconductor to being a conductor. Now, in addition to changing the electrical properties, you can also tune their optical properties, so their optoelectronic properties. So what I'd like to show you here is an example that our group has been working on for more than a decade now. This is polyaniline. It's called a polyelectrochromic polymer. Poly is multiple, electrochromic means it changes color with its different oxidation states. So in its most reduced form, it's called a glucomeridine base form of polyaniline, and it's transparent. This color, LB. If you extract 2 protons and 2 electrons, you get to the meridine base form of polyaniline. That's blue in color. And then if you further extract 2 electrons and 2 protons, you get to the permagranulin base form of polyaniline that's now deep purple in color. Now if you take this emeraldine base form of polyaniline and you expose it to protons, you're protonically doping the polymer, you get to this green electrically conducting state of polyaniline. So suffice to say that this polymer has multiple different oxidation states. These oxidation states have different properties, i.e. different colors. And this one's electrically conducting. And so in the decade and a half that we've been studying this conducting polymer, we've used it in glucose sensing applications. And in fact, this patent has been licensed by Abbott Diabetes in their glucose monitor kit. And Melda Sesson have been looking at them as strain gauges for monitoring building health. But this color is interesting because what it means is we can switch between these 2 colors. So again, this is the leucoemeraldine base form of polyaniline, and this is the most oxidized permagranulin-based polyaniline. What I'm showing you here is the solar spectrum. Okay, so this is the spectral irradiance as a function of wavelength. I highlighted here the visible range, okay, so 400 to 700 nanometers. In its fully oxidized form, you can see that this permagranulin polyaniline absorbs a whole lot of light, and it absorbs in the near infrared. But in its most reduced form, it actually doesn't absorb a whole lot of anything. So if we can toggle between these 2 oxidation states, we can create a curtain or a window that allows us to regulate visible light and near infrared light from coming in and from coming into the building. So this is to show you the color. This is the reduced form, and that's the most oxidized form. So you can see that the color contrast is actually very, very sharp. This is data quantifying the reversibility of the 2 oxidation states. So I'm plotting transmittance. 100% means it's completely clear, 0% is completely opaque. At a visible wavelength, okay, and you can see that I can toggle between being clear and being dark, back and forth, back and forth, back and forth. I can also do so in the near infrared. This is again transmittance, but in the near infrared. And again, I can go back and forth, back and forth, and back and forth. And the stimulus here is a voltage. Okay? This shows that it's stable over extended periods of time, and I can go back and forth, accessing the most reduced form and the most oxidized form. So here we've got a polymer that we can access its clear and dark state. It could be a very good window. So what I'm showing you here is a double pane insulated glass unit. Okay, it's got 2 glass units, and inside you've got an insulating gap. That's what's in your windows today. So the idea then is to put a layer of this polymer, or any electrochromic material if you will, but here I'm talking about polyaniline specifically, on the inside of the outer pane. And by applying a voltage, you can toggle it between its clear state and its dark state. And by going to the dark state, you can regulate how much light comes into the building. Now this is nice, because you can toggle it back and forth using a voltage. But this is bad, because you need a voltage, you need wires, you need power. And this external wiring has been estimated to add 15 to 20% in labor costs during installation. Having external wires means you're limited in terms of window operability. So this is limited these kinds of smart window technology to access retrofit markets. So wouldn't it be nice if you have an onboard power source? Something that's just there that can generate the voltage you need, so you can toggle back and forth between the 2 transmitted and the opaque states. You can think about solar cells. These are solar cells today. They're silicon solar cells on your roof. They absorb sunlight and generate electricity. But look at these solar cells. They're dark, they're opaque. They're not very suitable for the kinds of applications that I just talked about, because A, they're heavy, B, they absorb all the light. That's why they're solar cells. They're optimized to absorb light to generate power. So we need to think elsewhere. So what I'm showing you here is photon flux as a function of wavelength. I plotted this out to 3000 now. Again, the visible range is highlighted in this orange color here. This shows basically the integrated absorption of a silicon cell. Okay? And so you can see silicon, again, this to quantify what I've just said, is not very appropriate for these kinds of applications because it absorbs a whole lot of light. It absorbs the light that the windows seek to regulate. Okay? But just as a point of reference, I thought I would list here that the theoretical efficiency of these silicon solar cells that are on your roofs is 32%. The commercial cell efficiency is about 24%, and if you put them in modules, they drop a little to about 15%. So solar cells are inherently not very efficient devices. So we need to think elsewhere. So as a recap, we have a film, a polymer film, that can allow us to regulate light and near-infrared light as heat. So what's left in the solar spectrum then is really the near-ultraviolet. So we thought if we could make a near-ultraviolet solar cell that absorbs this light, it allows us to intelligently manage the sunlight. It allows us to generate power from this spectrum to then regulate the transmission of visible light and near-infrared light. So I think organics are appropriate for this kinds of application because organics have very narrow and tunable absorption. You can tune it by playing with the chemistry. So this is, again, silicon, just for contrast. These are dye-sensitized solar cells, so a slightly different technology, nonetheless requiring organic semiconductors. And look, depending on what dye you use, you can access different colors. Heliotech has made these transparent solar films or semi-transparent solar films. And again, it's by tuning the optoelectronic properties of these organic semiconductors. So the idea is as follows, and this I lifted from a Nature Energy article or a perspective that was highlighting our work. So the concept is as follows. We have an electrochromic film. What we'd like to do is to put a photovoltaic or a solar cell that's over the same footprint. This photovoltaic cell is going to absorb UV light and generate power. And we're going to use that power to then regulate the transmission of the infrared light and the visible light into the building. This is a fancier way of looking at it. If you have a double pane window, you can, for example, coat the PV layer on the outside. That then regulates the electrochromic window on the inner pane of the outer, on the inside of the outer pane. And then to go a little further, if you want to increase the energy efficiency, you can have a low emissivity coating that reflects this black body, long wavelength infrared. And so during a hot day, it reflects the infrared light outside. And during a cold day, when you heat up the room, it can reflect that heat back into the room. Okay? So that's the idea. So let me tell you how organic solar cells work before I show you the data. So an organic solar cell is a 2-electrode device. One of the electrodes has to be transparent because you need light to go in. And then inside, between the 2 electrodes, is your organic semiconductor. Typically, you have 2 organic semiconductors. You have a donor and an acceptor. So here I'm showing my solar cell upside down. This is my substrate. I have a transparent electrode, and I have my donor, an acceptor, and then my second electrode that I call a cathode. So as light shines in, the following happens. So I'm plotting my energy level. So these are the lowest unoccupied molecular orbital and the highest occupied molecular orbital of my organic semiconductor. And these are the work functions of my electrodes. When I shine light, it generates an exciton. An exciton is a tightly bound electron hole pair. This is very different from how silicon solar cells operate, because silicon solar cells, you generate free carriers. In this case, because organics have low dielectric constants, these hole and electrons are bound. And so they're going to migrate around until they find an interface that gives you enough driving force to split the electron hole pair. And when you then split the electron hole pair, your electron can migrate in the acceptor along its LUMO and be collected at the external electrode, and the hole can migrate along the HOMO of the donor and be collected at the external electrode. So now you begin to appreciate why these solar cells aren't very efficient devices. The efficiency of one such device is the compound efficiency of all these different processes. Light absorption needs to be good. This exciton diffusion to the interface needs to be good. Charge transfer to the acceptor needs to be good. And then charge collection needs to be good. So I've already told you the theoretical efficiency of a silicon cell. The record efficiency for a polymer solar cell is about 12%. Okay? For this reason, because the efficiency is a compound of these different processes. So if you look at the current density as a function of voltage, when you operate one of these cells, you get a curve that looks like such. This is what we call the power generation quadrant, and you want this quadrant to be as large as possible. A couple of figures of merit that I'd like to share with you so that we can refer to them later on in the talk. First of all, you have the open circuit voltage. This open circuit voltage, to a first approximation, is a materials property that depends on the donor and acceptor you've picked. It correlates with the difference in the energy level between the LUMO of your acceptor and the HOMO of your donor. Okay? So the bigger this difference is, the bigger your open circuit voltage is. We've got the short circuit current density, and that inversely correlates with the band gap of the absorbing material. And so now you begin to see that as we optimize the cell in terms of picking and choosing the donor and acceptor, as we increase the open circuit voltage, it almost always comes at the expense of the short circuit current density. Then finally, there's this loss here, this LUMO-LUMO difference. This, remember, is the driving force for us to split the exciton. And this needs to be about 0.5. Okay, so let me remind you, this is the solar spectrum. And of the solar spectrum, 45% of the photons is in the visible. 48% is in the near infrared and infrared. That only leaves 7% in the ultraviolet. So when I'm making my cells, don't expect me to hit or go beyond the efficiency record. Because we're dealing with only 7% of the photons, our cells are inherently inefficient. We're targeting it for a very specific, a different application. So this is work of Nick Davey, Anna Hispansky's graduated, and Melda says it. Both are in the audience somewhere. Okay, so this work started with synthesis. And this I'm really proud of because this was something I spent my sabbatical learning. I went to Columbia University in the chemistry department and learned how to do chemistry. And brought this chemistry back, and the students are now making these compounds. We like this chemistry because it's very modular. So there are a series of 3 reactions involved. This Corey-Fuchs reaction with the starting pentacene quinone gives us the brominated version. And then when we have this brominated version, we add a boronic acid or a boronic ester to decorate it. And then subsequently we can ring close to form these carbon-carbon double bonds. Now when I say this chemistry is very versatile, it's because there's a whole library of materials that you can buy with this boronic acid functionality. And so depending on what functionality you purchase, you can decorate your molecules. And remember, as you decorate them with different chemical functionality, you're changing the optoelectronic properties. Okay? So in this case, this is a benzofuran compound. And so we end up with a benzofuran decorated chlorinated compound. Now we've also chosen this chemistry because this molecule is non-flat. It's contorted. And you'll see why this contortion matters in a little bit. Suffice to say that basically when we form films, these films have no long-range order, they're disordered. And this disorder is good because it doesn't have any pinholes and we can make nice films uniformly over large areas. And I'll come back to this in a little bit. This slide is to show you that we can tune the optoelectronic properties. This is our precursor, our starting material, and depending on which boronic acid we use, so this is just a benzoboronic acid, this is a benzofuran and a benzothiopene, you can decorate it to access different compounds. And with these different compounds, you get different optoelectronic properties. So now that we have this, we can make a solar cell. These are the energy levels associated with these compounds. So this is the parent compound, CHBC. And then I'm going to show you work that's done on this benzofuran compound with the oxygen group. So this is the HOMO and the LUMO levels of the parent compound, and the HOMO and LUMO levels of this benzofuran compound. We need an acceptor, so we match it with C60. This is the commonly used acceptor. And so its chemical structure is shown here. The device is very simple. We've got 2 electrodes. ITO is our 1 electrode, and the aluminum is our 2nd electrode. And then we've got our donor and our acceptor. And so the current density as a function of voltage looks like so. And you can see that qualitatively it makes sense. Here, this gap between the LUMO of C60 and that of TVF is smaller than the gap between the LUMO of C60 and CHVC. That's why the black curve has a higher open circuit voltage. Now you can see that this band gap, the absorber, is larger than this, and that's why it's inversely proportional, so your short circuit current density is smaller. So to first order, it makes sense. And again, this emphasizes that optimization of the open circuit voltage and the short circuit current density is very difficult because you often get one at the expense of the other. So that's all good. We have a working cell. But if you look at the absorption, and if you were trying to make a transparent solar cell, you're in trouble. Here I'm plotting absorbance as a function of wavelength. And you can see that with C60 absorbs quite a bit in the visible. And so the transmittance curve is in the dashed line. And you can see that with C60, you're absorbing a lot of the visible here. So it comes to the fact that we need to replace C60 as the acceptor. We go back to our trusty chemistry. So here, again, this is our precursor. And this time, we've chosen boronic acids with electron withdrawing group. Remember, with these electron withdrawing group, we're lowering the energy levels. And so that's what we're doing here. And we've made different compounds, so I'm only showing you a quadrant of the chemical structure. That's the parent compound. We've made the chlorinated version. We can make the fluorinated version by starting with a fluorinated precursor. And then we can make the mixed chlorinated and fluorinated version. And this was all done by Anna Hispansky. So with this, we can characterize the energy levels. That's important. And we've done this in solution, in vacuum, on thin films, as well as done DOT calculations. I'm showing you here the energy levels of C60, so that's the acceptor for reference. And this is our donor, the TBF, the benzofluoride compound. And so as we add more halogens, we steadily march down in energy levels. And that's nice. And we can even quantify it. So the LUMO energy level drops by about 50 millielectron volts per fluorine and by about 70 millielectron volts per fluorine. This is nice because it generates a design rule for us, so we can predictively mix the next generation of compounds by knowing how much it affects the optoelectronics of the compound. Now with this, we can make devices. So we wanted to optimize, and we chosen initially to show you donor, and this 12Cl is the acceptor. So this is Nick Davey holding one of these films, so it's a stack of donor and acceptor. And now if you look at the absorbance and the transmittance, you can see that we're above 75% transmittance across the visible. So we're achieving what we'd like to do. But of course, this is only the thin films. We can make devices. So again, we have our two electrodes, the donor and the acceptor. That's our current density as a function of voltage profile. You can see immediately that the open circuit voltage is actually quite high. And that's because we've gone to wide bandgap materials. With wide bandgap materials, you're getting a big open circuit voltage. We can tune this. So this is C60, our acceptor that we started out with, and then the 12Cl data that I showed you earlier on. So as you can see, as we pull up the LUMO energy level, we're opening up this gap. And as we open up this gap, we're steadily marching across and increasing our open circuit voltage. Now, you can notice that the current here is quite small, resulting in very small efficiencies. And you would expect that because the UV is only 7% of the entire solar spectrum. And I would argue that this efficiency is not the right metric to measure how well performing our devices are. Instead, one should probably look at the efficiency, the wavelength-specific efficiency. So if you look at the wavelength-specific efficiency, and in particular looking at 400 nanometers, you can see that our devices work quite well, and the efficiency is about 16% efficient at 400 nanometers. So it's specifically tuned to absorb near UV light. You can look at power density as a function of voltage. This tells us the quality of the power that we're getting. So with a C60 device, we're getting a power of about 1.2 milliwatts per centimeter squared. And this power has a voltage of 0.64 volts. But with our cells, we're getting comparable or slightly higher power, but these power are at much higher voltages. And this voltage is now nice because we can use it to modulate the switching of our electrochromic cells, okay, of our electrochromic polymer. Before I show you the integration, I thought I would mention stability because we are absorbing UV light, and we all know UV light is harmful for organics. This data shows very stable performance in our solar cells. The open circuit voltage especially stays pegged and pinned. And this is a strong indication to us that the compounds that we're using to absorb light is not degrading over time. Because as it degrades, as we lose chlorines, it should move the energy level, and we should see a difference in the open circuit voltage. The short circuit current density and the power density falls a little bit. We call this the burn-in period. And that's typical of cells, and we see this in low band gap polymer cells, etc. Even in silicon cells, you see some of this. So this is nice. Now this is the data that we're most excited about. So for the organic electronics community, when we build photovoltaic cells, the standard test cell is about 0.2 centimeters squared. Okay? And that's because there could be a lot of defects in these cells. And scalability is very, very challenging. If you remember, I told you that our films are amorphous. When they're amorphous, they don't have grain boundaries. They don't have defects because everything is defective effectively. And so because of that, we get rid of these pinholes. And so our yields are 100%. And we can scale very, very nicely with area. So this is the current density as a function of voltage curve from 0.2 centimeters squared to 2 centimeters squared. And here I'm plotting power as a function of area, and you can see it scales very, very nicely with area. For two reasons. One is the amorphous scope that I mentioned earlier on. And the other is because our power is low current. And the losses scale with current squared. And so we eliminate this problem as well. And for comparison, these are polymer solar cells that are crystalline. Okay, so they have the defects that I was telling you about. They see a 20% reduction in fill factor and a 24% reduction in power density when we scale over the same areas. So this is high-resolution cross-sectional microscopy that was carried out by Nan Yao over at PRISM in the IAC. You can see the pristine interface, okay, and you can see that there's no long-range order in these donor and acceptor layers. So we got a little more ambitious, and we decided to scale it further. And here's a 10 centimeter squared cell. It's got a slightly different electrode motif, and that's because we wanted something that didn't have high contact resistances compared to ITO. But you can see again, even when we go to 10 centimeters squared, the power scales very nicely with area. And 10 centimeters squared is significant because once you can make a 10 centimeter squared cell, you can now connect 10 centimeter squared cells together to make a module. Okay? So this is significant. All right, so what I've shown you so far is that we can modulate the visible light and near-IR light with a polymer film. I've shown you that we can absorb UV light and generate power that has a significant voltage that we can use to modulate the visible light and the near-infrared light. So let me show you in the remaining time I have how we can integrate the two together. So the idea is as follows, right? We have our solar cell, and then we're going to put this electrochromic polyaniline on top over the same footprint to make a cell that's self-powered, right? A self-powered smart window. And this was just published in August in Nature Energy. And so in doing so, we eliminate any need for external power sources or any need for external wiring. That's the idea. So this is our solar cell stack, right? So we've got our electrodes, we've got our donor and acceptor layer, and then there are some interfacial layers in there. This is our electrochromic window. You saw the characteristics of polyaniline. We can change the color of polyaniline through a redox mechanism. So what that means is we're shuttling electrons back and forth. So you need an electrolyte that helps you shuttle electrons back and forth. And you need a counter electrode that basically accepts the electrons when polyaniline is giving out the electron, and one that spits out the electron when polyaniline wants the electron. So, when this is oxidized, when polyaniline is reduced, this counter electrode is oxidized. And we chose PEDOT-PSS, this is another conducting polymer, because when this is oxidized and when this is reduced, both are transparent. And the opposite, when polyaniline is oxidized, and when P dot is reduced, they're both colored. So this adds to the contrast that we have between the bleach state and the transparent state. So the idea is then to hook them together. So this is Melda Seson's work. So that's the polyaniline. The liquid is the electrolyte. This is our very first demonstration, and you can see the solar cell that's here that's powering the switching of this electrochromic film. So this is as we go from dark to transparent with the solar cell turned on, or with the light turned on to illuminate the solar cell. And then this is as we go from bright to dark. Again, this is with a liquid electrolyte, and the counter electrode here is indium tin oxide. So this is only half a window, if you will. So then we got ambitious, and we said, okay, the liquid needs to go. We need a gel electrolyte if we're going to make a window. So this is with a gel electrolyte. This is, again, the prototype. We have a 1 centimeter squared solar cell right here, and we're connecting it to our electrochromic window. And you can see the transmittance between the bleach state and the colored state is quite nice, both in the visible and in the near infrared. So the switching, of course, depends. The contrast will depend on the voltage that you apply to the system. And this is nice because it gives the user some control. Right? You might want it dark one day, you might want it not so dark another day. So by switching the voltage, you can switch between the contrast, between 60%. 20% or less. You can do the same on the onset by changing the film thicknesses, because if you're thinking about a privacy application, you might want the contrast to vary as such. But if you're thinking about architectural glass and you want transparency, then you might think about using this combination of film thickness. Suffice to say that we can tune the transmission of light depending on the thicknesses of P dot and polyaniline. This is to show that the window can be operated stably, and so you can go back and forth between the bleach state and the colored state. And so with electrochromic materials, what's nice is to access that oxidation state, you need a pulse. Okay? A pulse gets you there. When you have no bias, it basically slowly bleaches. And so we determined that basically every 15 minutes, you need to pulse it a little bit so it brings it back to the original oxidation state to maintain the color. But as long as you do that, you can maintain the transmittance and you can maintain the opaqueness at where you'd like it to be. So this is the solar-powered electrochromic window. The solar cell is 1.4 centimeters squared, and here the electrochromic window is 2.25 centimeters squared. And so you can see between the colored and the bleach states, the contrast is quite nice. So this shows you the switching times and the current that's needed. So this is a transmittance. So this describes the clear state. This is the colored state. And this is the pulse that's needed to get you to that respective oxidation state. You might ask, well, do you have enough power to regulate this? And the answer is yes. So it turns out that with our solar cell, with the efficiency that I was just telling you, if it absorbs light and generates power in 6 minutes, that amount of energy is enough to power your electrochromic window over a 24-hour period. So what this is saying is, if we have a small capacitor or a small battery, what we can do is store the rest of the power and operate the electrochromic window in the dark on a cloudy day when it's raining. So where are we headed? At the outset, I said that polyaniline has multiple different oxidation states, and we've only used the extremes, the reduced and the oxidized oxidation state, and that's shown here. Right? There's this green emeraldine salt oxidation state that's quite interesting because it doesn't absorb a whole lot in the visible, but it absorbs in the near infrared. So you can access this cool mode where you're absorbing infrared, but you're letting visible light in. So that's where we're headed. We're hoping to make these dual band electrochromics that allows us to independently access these different states so we can control how much light, how much visible light, and how much near infrared light comes in. This is preliminary data to show that the switching is quite nice and stable. So these are the 3 oxidation states. This is in the visible and in the near infrared. And you can see that you can access them very, very nicely. So we're going to try and integrate these. So in summary, I hope I've shown you that this chemical versatility that the organic electronics community is very excited about is really nice because it has allowed us to access a family of compounds with tunable optoelectronic properties. Instead of making things more crystalline, which is what the community is doing, we've actually taken a step back and made things amorphous, so no long-range order. Sure, our charge transport has suffered a little bit, but what that has enabled us to do is to make films that don't have any defects, so we can scale very nicely with area. And that these near UV absorbing solar cells can effectively drive the switching of these electrical polymer over the same footprint. So where does that leave us? Well, the residential and commercial buildings consume about 40% of the US electricity. And so this cost exceeds 260 billion annually, not to mention the 30%, it being responsible for 30% of carbon emissions. With these smart windows, we can reduce consumption by 10 to 20% through regulation of visible light and heat. And so this idea of onboard power, it eliminates external wiring, so it can reduce installation costs by about 20%, increases window operability, and we can think in the future about making these as films or laminates so that we can access the retrofit market. So let me thank my group, the funding sources, and call out Nick Davey, who was responsible for the transparent solar cell work, and Melda Sezin, who was responsible for the integration with the electrochromate material. So before I finish and take any questions, I thought I would make two quick announcements. One is the eAffiliates annual meeting is coming up. This is our 6th annual meeting, and annually it's drawn about 200 people from outside, from inside. Fred Krupp from Environmental Defense Fund is our keynote speaker, and we have a lightning round on coastal resilience involving Lynne Lu and Esteban, I forgot his last name, Rossi Hansberg, I think, who's going to be doing the lightning round. So I think this would be of interest to you. It's free. Please register so we have the right amount of food, but please come and join us. And then for the students in the audience, we have a scavenger hunt this Friday. Come and learn more about us. Just RSVP so we get the right amount of pizza. So thank you again, and happy to answer any questions.
Questions?
Oh, okay.
You didn't mention polarization, but it did make me think of sunglasses that
Yeah.
change. What's the fundamental difference between sunglasses that we had in '80?
Yeah, so
Can you repeat the question?
So what's the difference between this and sunglasses that change? So I'm not thinking so much about sunglasses, but these transition lenses, when you go outside, it goes dark.
Yeah.
Those are photochromic materials. So they're sensitive to light as opposed to an external bias. There, the switching is much slower, and the switching is really bipolar. You can't access anything in between. So that's the difference. But the stimulus is different. Okay? And with sunglasses, it's different because it polarizes light from this way versus that way.
But so is that a desirable feature that you might want polarization?
So I started thinking about that because I was giving a talk somewhere, I forget where now, and somebody had asked about polarization. I think what you can do is pattern strips, and then depending on the resolution of the strips you pattern, you can have it be sensitive. You can have it polarize X-rays. You can have it polarize UV. You can have it polarize IR, and then the stimulus would be a voltage. You can certainly do that, but you'd have to pattern it into strips. Yes.
Do you see a practical limit to the size of glass that this could be printed on? You're working on a very small scale right now. Could
Right.
this be huge sheets of glass?
Yeah, so I mean, what we envision is, now that we can make 10 centimeters squared, what we can do is we can connect 10 centimeters squared in parallel to make modules, and that will be limited by the size of the glass. I mean, we can get thin glass that are very, very large areas, the kinds that are used to produce, for example, whatever, flexible TVs and things like that. What is it, Gorilla Glass or something like that? Or you can even print it on plastics, right? I think the key, and for us, the threshold was getting to the 10 centimeters squared, because then you can connect it. So then, in principle, you should be able to do everything else that one would imagine needing to do. Yes,
Have you tested this with tempered glass?
tempered glass.
Well, if you're talking about architectural insulation, they have to be tempered glass.
Okay, and what's the difference between tempered glass and non-tempered? Well, I mean, I know what's the difference, but in terms of, I guess what I care about is how smooth that glass is. As long as that glass is smooth, I can deposit a 20 nanometer film. I should be able to make these cells. So the question is, what's the difference in smoothness between tempered glass and the regular glass? And I don't know the answer.
One of the things with tempered glass is it's not necessarily planar on the two surfaces, maybe like that.
Oh, well, I mean, don't know the answer to that, but I mean, the way we deposit these materials, it's a conformal deposition process, right? And so it's an evaporation process. It will coat conformally. So I think it'll be okay, but
The
we'll have to
spacing
test
will be
it.
changed
The spacing will change.
between the surfaces.
Oh, but that doesn't matter, right? Because I mean, we're going to make our entire device set on one surface.
One surface.
That's
Okay.
right. So as long as it's conformal, we should be okay. And the deposition methods we've chosen are all conformal. Well, they deposit conformal films. I'll go up there first.
Earlier on, when you were talking about the compounds you developed, you said that you made them more soluble. So I was wondering, say there's a disaster, a building made out of these windows is demolished and it's exposed to water. How do you think these chemicals are going to affect the environment if they were to get into water and into a natural area?
So these compounds, these specific ones that are used in the solar cells are not soluble. The polyaniline is water soluble, but once you make a film, it doesn't go back into solution very easily. So that said, we're only using 20 nanometers. There's very, very tiny amounts in there to begin with. And these compounds, I think if you talk to anybody who's in an oil and gas company, they look at these compounds, and it reminds them of compounds that exist in tar. So it's, I mean, we don't know the toxicity, but everything points to, I think it'll be okay. So that's something that we'll still have to test. Yes?
So could you combine this with an energy-producing solar cell and
Combine, what is this?
so combine what you're doing to filter out
Uh-huh.
the heat,
Yeah.
basically heat advantage, with another kind of layer-on solar cell that would also produce energy for electricity use?
So it depends on what you're trying to do. I mean, you can optimize for power production, in which case you can absorb all of the light, which leaves none left for you to regulate. Or you can optimize for visible transparency, in which case you generate enough power to power the electrochromic window. Now, you can put the solar cell on the roof and wire it to your electrochromic window, but that's precisely what we were trying to avoid. We didn't want the wire.
Now, I'm just wondering, I mean, there's kind of a trade-off here, right? If you
Yes,
get-
absolutely.
If you get 8% from the solar cell, you might be able to run your air conditioner,
Yeah, I mean, absolutely there's a trade-off. And the trade-off is between power generation and transparency, right? Yeah.
One of the semi-transparent photovoltaic medium is amorphous silicon, which if you make it relatively thin, can have relatively poor efficiency yet good light transmission. We've done this at Chromate.
Okay.
Is that something you considered at all?
No, we've not. We wanted to stay with the organics because then we can tune it. In fact, what we'd like to do is to tune it so that it further absorbs into the UV. I think the nice thing about organics is you can, I mean, once you get a handle of it, the chemistry, you can tune it and move it around. In fact, there are others in the community that have demonstrated near-infrared solar cells. And those, the voltages aren't as high as ours because they absorb low energy photons, but they generate more power, if you will. So, I mean, it's all a trade-off. We decided we want to go with the more energetic photons. We wanted to go with something with which we can generate enough power to power our smart windows. Yes, Lars?
Then, if you think of cities, one of the major determinants of exchange of energy or in cities is the heat exchange. Not only through windows, but primarily through built materials. So, you know, a black structure absorbs heat, which is great when it's cold outside, which is a problem on a hot day. Could you imagine getting some kind of polymer that you in fact spray over entire buildings? You can flip the building. So what
Talking
you would,
about black body radiation.
no, what I'm talking about is what you would need is a reflecting film underneath. And then, and then you could actually, instead of just, because even for a single building, the energy coming in through the window is a minor thing that air conditioning has to deal with that, but eventually it's what's absorbed in the whole building, right, and then radiates in. So if you can manipulate that,
So
then
on
maybe
the
an even greater.
non-window facades.
Yeah, it would be an even greater. I know 3M does a lot of these things, right?
Put that on your list at least. I'm just kidding. Yeah, no, I mean, so the low emissive coatings do that to a certain extent, but they are for the windows. They are for the windows.
No,
Because I
that-
mean, if you have building
you get my
facades,
point, right?
you have thick walls, they can act as insulator, right? So they're gonna be sinks, essentially. So here, it's really talking about window losses, and you saw how much loss we could avoid if you can insulate the window properly.
Oh, I understand the window. I'm arguing a bigger perspective here. Yeah. Okay, all right.
Denise?
So I think it's totally amazing. It sounds like it has great potential. It's really fascinating. But I'm wondering, when you think about deploying this on a large scale, do you have any idea of what the costs might be? And then not only, as Lars was saying, the effect on just the windows and the amount of light that's transmitted and using it as a mechanism for reducing your air conditioning and heating costs, but also, is it possible to use this type of device on a larger surface where you want to use that surface as a way to generate electricity? So rather than having those silicon panels attached to phone poles all over the place, you could imagine painting your buildings.
Yeah,
with
so
solar cells.
there were multiple
Organic solar
questions
cells.
folded in there. So the last one that I remember, so I'm going to answer that one, and then you'll have to remind me what you had asked before. So in fact, we were thinking in terms of next generation, where we want to take this. Organics are very good at absorbing diffuse light, meaning that inside the room, it should work nicely. And so now we have not tested this, but the idea is to put it inside the room. It could be ubiquitous, transparent, invisible, whatever you want to call it, and then you can power these smart devices, right? An amplifier, your Alexa, your Echo, whatever. It's not going to generate a whole lot of power for you, but it's going to generate power, portable power, where you stick the laminate, right? So that's what we're hoping to explore next.
The small quantities of power that could be
That's right, that's right. For things that need small powers, right? So you have your Alexa, you have your routers, your wireless routers and things like that don't require a whole lot of power, but they require power right there. Can you stick a patch that generates power for that? It's not going to power air conditioning. It's not, right? I mean, we only have 7% photons that we're working with. So there, I think you need to think about broad absorbers. It's a completely different application.
Let's take one more question.
Yes, sir.
Question about so when the window becomes non-transmissive, it's absorbing that energy. Is there a concern that it heats up enough to either change the properties of the film or to degrade the film?
So that's something that's been brought up, and we need to look into that. We don't know the answer to that quite yet, but I mean, it's generating power using the UV light. So where we're concerned about is really the infrared that's coming in. So, but that's something that we need to really look into, and we haven't yet. Good point.
Great. Before I say thank you one more time, please clean up after yourselves. If you brought in anything with you, please take it out with you so someone doesn't have to clean up after you. And after that, I will say thank you very much.